Ladies and gentlemen, distinguished guests, welcome to the 51st George Gamow Memorial Lecture. I'm Paul Beal, Professor of Physics and Chair of the George Gamow Memorial Lecture Committee. This public lecture series honors George Gamow, a professor of physics at the University of Colorado from 1956 to 1968. The Gamow Memorial Lectures were initiated in 1971 by the Department of Physics, and in 1975, Professor Gamow's wife, Barbara, left a bequest to the university, establishing an endowment for the purpose of maintaining these free public lectures in perpetuity. All subsequent lectures have been funded by this generous gift. I would like to thank Igor and Elfrida Gamow for their continued support for this wonderful program and for establishing an undergraduate physics scholarship in their names. George Gamow was one of the leading scientific figures of the 20th century. He made seminal contributions to nuclear physics, astrophysics, and molecular biology, and he was a prolific writer. George was born in Odessa in Crimea in 1904. At the age of 24, Professor Gamow was the first to use quantum mechanics to describe nuclear physics. He produced a complete and quantitatively accurate explanation of radioactive decay in terms of quantum tunneling. Remarkably, this was only 2 years after Heisenberg and Schrodinger had developed quantum mechanics to explain the properties of the atomic structure of hydrogen. In the following few years, Gamow developed theories for thermonuclear reactions that powers the sun, and first proposed the nuclear drop model that was instrumental in the theory of nuclear fission. George and his wife, Rose, defected to the West in 1933 after attending the 7th Solvay conference that brought the greatest minds in physics together to discuss radioactivity and nuclear physics. From 1934 to 1956, George was a professor of physics at George Washington University. The annual conferences he established at GW and later at the University of Colorado attracted leading scientists from around the world. In 1948, George and his graduate student Ralph Alpher published the first paper on what has become known colloquially as the Big Bang Theory. In their paper, they calculated the abundances of the light chemical elements created in the Big Bang 13.8 billion years ago. The paper was published on April 1st, 1948. Perhaps not coincidentally, George, always the whimsical jester, added his friend Hans Bethe's name to the paper as a pun on the Greek alphabet. The paper is still widely known as the Alpher-Bethe-Gamow theory of primordial nucleosynthesis. In further work, Alpher and Robert Herman extended the theory and predicted that the universe should be filled with thermal microwave radiation left over from the Big Bang. This cosmic microwave background was discovered by Arno Penzias and Robert Wilson in 1963. In 1954, George turned his mind to explaining the genetic code. He and James Watson created the interdisciplinary RNA Tie Club, which helped to unravel the mysteries of DNA. Gamow was the first to show that a 3-letter nucleotide code was sufficient to define all of the known amino acids. Professor Gamow is perhaps best known to the general public for his many successful books that explained even the most arcane concepts of science and mathematics. George Gamow's Mr. Tompkins series introduced millions of people to physics and biology, and I still have the copy of 1, 2, 3, Infinity that my parents bought for me when I was in junior high school. It is dedicated to and kindly autographed by his son Igor, quote, who wanted to be a cowboy. In recognition for the importance of his popularization of science, the United Nations awarded him the Kalinga Prize in 1956. That same year, George joined the faculty of the Department of Physics at the University of Colorado. He quickly became a campus leader, and his teaching and writing influenced a new generation. He published over a dozen additional textbooks and popular books on science. George Gamow died in 1968, but his legacy continues. His campaign to create a modern physics building at CU came to fruition, and the physics office tower bears his name. Barbara Gamow's bequest stipulates that the Gamow lecturer, quote, shall be a person widely known for scholarly achievements in one or more of the fields of physics, astrophysics, mathematics, biology, chemistry, geology, or engineering, and shall be known for his or her excellence in interpreting science for the general public. Tonight's lecturer fits that description perfectly. He gratefully accepted our invitation to speak tonight since, quote, George Gamow played a huge role in getting me hooked on physics when I was a teenager. It is my honor to introduce Professor Michael Shull from the Department of Astrophysical and Planetary Sciences, who will introduce tonight's speaker.
It's wonderful to see so many people here. This is a great turnout. It's my privilege to introduce the 51st Gamow lecturer, Professor Kip Thorne from California Institute of Technology, which is my alma mater, Caltech. Just a few words about his background and a few stories, and then we'll turn it over to Kip. Kip was born in Logan, Utah, and he got his undergraduate degree in physics at Caltech, went on to Princeton for his PhD, working with Professor John Wheeler, who was a fabulous proponent of relativity and general relativity and cosmology. For 42 years, Kip was on the faculty at Caltech, and I was privileged to have a class from him my senior year. So 1967 to 2009, 52 PhD students, amazing, including some very famous professors of their own right. He retired in 2009 to start a new career, as he calls it, in writing, movies, and continuing in science, thank goodness, because that science really paid off, as we're going to hear tonight. A couple of prizes, he's won many, but I'm going to highlight 4 of them. The Shaw Prize last year for astronomy, the Gruber Prize in cosmology last year, the Breakthrough Prize in fundamental physics, and my favorite, the James Joyce Award for Human Endeavor, given by University College Dublin. I really like that one. So on to what he's done and why we're inviting him here tonight. He was the co-founder with Ray Weiss and Ronald Reaver, who unfortunately passed away in March. The 3 of them, with a lot of help, founded the Laser Interferometer Gravitational Wave Observatory. That mouthful we'll call LIGO. And you'll hear a lot about LIGO tonight. Last year, they announced the discovery of something very exciting to both physics and astronomy, the merger of 2 black holes to form one even bigger black hole. And they found the signals with gravitational wave interferometers. So this has been a love of Kip Thorne's for over 50 years, I think. He was talking about it in our class back in 1972. He wrote textbooks about it, the famous Gravitation textbook by Misner, Thorne, and Wheeler, a popular book that is still out called Black Holes and Time Warps in 1994, and then a popular book that many of us have seen recently called The Science of Interstellar. And I don't mean interstellar gas, I mean the movie. So as you will find out, Kip shifted gears in 2009 and started developing sci-fi treatments, they call it in Hollywood. Before the screenplays, there's the idea, then the treatment. So Kip worked with Linda Obst and Christopher Nolan to develop the science case behind the movie, which was fabulously popular, Interstellar. I'm reminded of a story that my wife told me. She was talking to a young woman in a different field and asked, do you know who Paul McCartney was? who had gone on to other things. And the answer was, yeah, he used to work for this old band called the Beatles. Well, Kip has had a similar move from his fundamental work in gravitational physics, astrophysics of neutron stars and black holes, and gravity waves, and now is developing wonderful screenplays or helping people work on them in the science fiction. So I'll close with a quote, a very prescient quote from this book he wrote 23 years ago, Black Holes and Time Warps. He said, gravitational wave detectors will soon bring us observational maps of black holes colliding. Supercomputer simulations will attempt to replicate the symphonies and tell us what they mean, and black holes will thereby become the objects of detailed scrutiny. What will that scrutiny teach us? There will be surprises. So get ready for some surprises. Kip? Thanks, Doc.
Thank you very much. I will begin with a quotation from my friend Stephen Hawking. Can you hear me? I didn't get the answer. Okay. So, as Mike said, I grew up in Logan, Utah, and in 1953, I went to a bookstore in Salt Lake City and discovered this book, 1, 2, 3, Infinity. I took it home, I read it, and I was just totally captivated. It described physics, astrophysics, cosmology, mathematics, a glorious world of ideas and of observational results and of predictions. I reread it a second time, became even more captivated. After the third reading, I decided I have to be a physicist when I grow up. I have to understand all of these areas, physics, mathematics, cosmology, astrophysics. Particularly intriguing to me, and it was etched in my mind from the first time I saw it onward, was figure 26. This is a typical Gamow drawing, his own art in his books, of a family looking at the projection into our three-dimensional universe, the projection of a four-dimensional cube. You begin with a square, say. That's a two-dimensional cube, if you wish. It's a two-dimensional object whose legs are all perpendicular to each other and all have the same length. You then go to 3 dimensions, and you get the usual kind of a cube. And then you ask, what if we lived in 4 dimensions, what would a cube look like? And that's what it would look like. And I sat and I stared at that for hours on end, trying to understand it, trying to comprehend it. I also learned that it has a more technical name, a tesseract. Some of you know about a tesseract from the child science fiction book, Wrinkle in Time, where a tesseract plays a role as well. And so I was so enamored of that in high school, after having learned about axiomatic Euclidean geometry in 2 dimensions and having had the teacher show us a little bit about how it works in 3 dimensions, my high school science project was not building a telescope. It was trying to work out axiomatic Euclidean geometry in 4 dimensions, all motivated by this figure etched in my mind from reading George Gamow's book. Well, so I did go on to become a physicist who works in astrophysics and cosmology. I don't work in mathematics, though my high school science project was that. And I went through undergraduate school at Caltech and then graduate school at Princeton, returned to Caltech on the faculty, and shortly after returning on the faculty, I did some research and wrote a paper about primordial element formation, the birth of the elements in the Big Bang, something for which George Gamow had some big influence. Primordial magnetic fields that originated possibly in the Big Bang, and the isotropy of the universe having the same kind of a form when you look in all directions. A few days after that paper was published, I was overjoyed to receive a letter from George Gamow. It said, "Dear Kip," I think I had met him once at a conference at that point, just in passing. "Dear Kip, I have some questions." A series of tough questions about this paper. So I responded as best I could. I sent it back, and I told him in a PS at the end, I'm really a physicist because of you, because of your book 1, 2, 3, Infinity, which affected me so profoundly. I read it 3 times as a young teenager, and that is what got me hooked. And George, by return mail, sent me a copy of 1, 2, 3, Infinity in Hungarian, inscribed to Kip so that he would not be able to reread it a 4th time. George, May 1968, the year of the pulsar, the year in which pulsars were discovered. So that is one of my most treasured possessions. When I was invited to give this lecture, I looked at my bookcase, and within 10 seconds I found it sitting in my bookcase with George's signature on it. So now you understand why I was so overjoyed to be honored with this invitation to lecture here. George's impact on me was truly profound. And so now I will back off and turn to the main topic for this evening. Oh, no, I guess I won't. I want to do one other thing. I wanted to say that I decided early on in my career that I wanted to pass on to the next generation of students and young people George's message to me of the beauty and the power of science, and particularly of physics, cosmology, astrophysics, mathematics. And so one of the vehicles I used for that was the movie Interstellar. And in Interstellar, late in the movie, there is a tesseract as seen from the inside. You have to read my book about the science of Interstellar in order to understand it. Or in order to understand a lot of the movie. But the key point is that for me, this movie was a way to lure young people into becoming fascinated with science. And then a book about the science in the movie was the hook to hold them in fascination and encourage them to move further in a study of science. And since the movie was seen by roughly 100 million people, how else could a physicist reach that kind of an audience? But that to me was basically my attempt to do for the next generation what George did for me. So now I'm ready to move on to gravitational waves. 1.3 billion years ago, at the same time as here on Earth, multicellular life was just spreading across the globe. But in a galaxy far, far away, two black holes circled round and round each other. Could you turn the lights off, please? Two black holes circled around and around each other, pulled together by their own gravity. Lights off as far as possible. And here you see the shadows of the black holes against a distant star field. The star field is actually very uniform, but the bending of starlight around the black holes by the extreme gravitational pull of the black holes and their curvature of space and time causes these patterns. They are lensed like objects are lensed by a lens in a camera, but they are lensed and focused into this fascinating pattern. And here you now see them going around and around each other. Out here you see this swirl of what is called an Einstein ring associated with the gravitational lensing. As they traveled around each other, they emitted ripples in the fabric of space and time called gravitational waves that carried away energy, causing them to spiral closer and closer together. And then ultimately, in a gigantic collision, they collided and they merged. And that collision was so energetic that it converted 3 solar masses of the black hole's energy into pure gravitational waves. It is as though you had annihilated 3 suns and converted all of their energy into gravitational radiation. And that gravitational radiation came off so fast during the collision, in about a tenth of a second, that the power output during the collision, the amount of energy that came off in a unit time during the collision, was 50 times higher than the total luminosity of all the stars in the universe put together. But only briefly, for a tenth of a second, but that was long enough to give off 3 solar masses of energy. So the gravitational wave, a burst of gravitational waves from this, then traveled out of the galaxy in which the black holes lived, into intergalactic space, across the great reaches of intergalactic space, and into the outer edges of our Milky Way galaxy, arriving there 50,000 years ago, when the Neanderthals were sharing the Earth with our ancestors. The waves traveled on across our galaxy and arrived at Earth on 14th of September 2015. They arrived initially at the tip of the Antarctic Peninsula. They traveled upward through the Earth, totally unscathed, emerged at the LIGO Laser Interferometer Gravitational Wave Observatory in Livingston, Louisiana. 10 milliseconds 7 milliseconds, 7/1000th of a second later, they came up through the Earth at our gravitational wave detector in Hanford, Washington. The data from that were analyzed automatically by a computer program which identified this as a possible source of gravitational waves, and that then went to humans to stare at for a long time. The team, for 5 months, the LIGO team, which is 1,000 people by now, worked hard with those data, tried to understand them, tried to be absolutely sure that this was gravitational waves and nothing else. These instruments are very complex. I won't talk in detail about them, but they are so complex that they have 100,000 data channels coming off of each instrument. Each channel carrying information about either something going on in the environment around these detectors or something going on in the interior of the detectors. And so all those data had to be examined to be sure that there was no sign of anything being wrong, that everything was in accord with what you would expect from a gravitational wave. And when the data were completely clear, the case was ironclad, the result was announced. And it made front page news in all the major newspapers in the world. From New York to Boulder to New Delhi to Moscow, everywhere around the world, Bakersfield, California, the Logan Herald Journal, everywhere. And it was really quite remarkable. Within 2 days after this, Ray Weiss, who co-founded LIGO with me, was in a subway train in New York City. And he, with his son-in-law, and they saw this couple here. This is a photograph. It's not a drawing. This couple here in front of a sign there, which says, scientists have found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet. And the day after our announcement in the New Yorker, 2 birds, one speaks to the other. You have to know as background that the sound that the gravitational wave signal made, if you put it on a loudspeaker, was whoop, it was a chirp. And one bird says to the other, was that you I heard just now, or was it 2 black holes colliding? So this has become part of world culture amazingly rapidly. I never expected anything like that. So how did we get here? Well, I'll give you a brief, very brief description of how we got here. It's really a long and tortured story. I won't torture you with much of the detail. But it begins with Albert Einstein in 1916, who predicted the existence of these gravitational waves and told us what they were like. And he said that you can think of the gravitational waves as being stretching and squeezing of space in directions perpendicular to the direction the wave is propagating. So here the wave is propagating into the screen, and space is stretching horizontally, squeezing vertically. The next half cycle it stretches vertically, squeezes horizontally. What that means in a different language is that if you have 2 inertial reference frames, one here and one there, and that means that particles that are initially at rest remain at rest in those inertial reference frames. Those inertial reference frames move back and forth with respect to each other. And that's the stretching and squeezing of space. And that means that particles that are at rest with respect to each other initially, they will be moved back and forth just the manner that you see with these dots. You can think of those dots as particles that are outside the Earth, up in Earth orbit, but they're being pushed back and forth relative to each other by these gravitational waves. They are riding on this stretching and squeezing space. Now, Einstein also said in his June 1916 paper, he said at the end, and I paraphrase, these waves will be so weak by the time they reach Earth that humans will probably never ever be able to detect them. But things changed by the 1960s. And Joseph Weber at the University of Maryland was the first person to really recognize the degree of that change and to have the chutzpah, the courage, based on that change, to build the first gravitational wave detectors. He really was the father of our field. And the changes that had occurred is we now knew about two kinds of objects that we didn't know about before that would be much stronger sources of gravitational waves than anything Einstein knew of in 1916. Black holes and neutron stars, about which I'll speak a little bit later. And technology has changed. We now had lasers, we had computers, we had tools that Einstein had not dreamed of in 1916. And with those changes, then, Weber pioneered our field of gravitational wave detection. And let me say, I was personally inspired by Joe. I went hiking with him in the French Alps in 1963 when we were both at a summer school there, and he was lecturing about gravitational wave detection and the attempt to search for gravitational waves. And it was in those private conversations hiking in the Alps that I really became enamored of this field. And so in 1966, 3 years after that, when I joined the faculty at Caltech, I built a theory group working on black holes, neutron stars, and gravitational waves. And by the early 1970s, I and others of my colleagues elsewhere had come to an understanding of the great power that gravitational waves would have if you could harness them for astronomy. And the key thing, as we saw it, was the differences between the electromagnetic waves that are used by astronomers for almost all their observations and gravitational waves. Electromagnetic waves are oscillations of the electric and magnetic fields that propagate through space and time. Gravitational waves are oscillations of the very fabric of space and time itself, the stretching and squeezing of space. That's just one aspect of a gravitational wave. I'm not going to tell you much about it, but time also speeds up and slows down in a certain sense in a gravitational wave. So space and time are affected. The electromagnetic waves that astronomers see are almost always incoherent superpositions of emission from individual particles or atoms or molecules, whereas gravitational waves are coherent emission by the bulk motion of large amounts of matter or energy, mass and energy. Completely different kind of emission process. And for example, a black hole is made of pure energy associated with the warping of space and time. There's no matter involved, actually. But its energy produces the gravitational waves as two black holes go around each other. And because there are no particles or atoms or molecules, it produces no electromagnetic waves. The electromagnetic waves that astronomers look at are all too easily absorbed and scattered by matter intervening between the Earth and the source, whereas gravitational waves are never significantly absorbed or scattered, not even near the Big Bang, the Planck era, when space and time came into being. With these differences, the implications were that many gravitational wave sources would never be seen electromagnetically, and there will be great surprises when gravitational waves astronomy comes mature. And so that was the case, as I saw it, based on my work and that of colleagues in the early 1970s, for really trying to build gravitational wave detectors. Ray Weiss was a friend and colleague of mine at Princeton when I was a graduate student. He was a postdoc. I went to Caltech on the faculty. He went to MIT on the faculty. And in 1972, at the same time as I was developing the theoretical understanding of how marvelous gravitational waves would be for astronomy and physics, he published, I say that in quotation marks, he wrote the most powerful paper I think that I have ever read, technical paper, in which he described a design for a gravitational wave detector very different from the design that Joseph Weber had been working on. A design that he argued would be capable of detecting gravitational waves if you just made this object big, like kilometer scale. Now, he not only described this design, he also went through and identified all the major noise sources that this kind of a gravitational wave detector would have to face and identified ways to deal with all those kinds of noise it would have to face. And then, having done that, he estimated the sensitivity of the detectors, compared that with the kinds of predictions of how strong the waves would be that I and my other theorist colleagues were making, and made the case that this could succeed if you could build these big. His idea was the idea that, with some modest changes, ultimately became LIGO, our gravitational wave detectors. You had 4 masses that hung from overhead supports. You're looking down on them. The red is a laser beam. These masses are pushed apart. They're hanging by wires. They're pushed apart by the gravitational waves when those are being pushed together. When these are being pushed apart, these are being pushed together. And the laser beam is sent in, split by a beam splitter, goes through a hole in this mirror, bounces back and forth many times, returns. Same thing for that beam. That recombines, and you look at the intensity of the light. It goes to a photodetector down here. This is what is called optical interferometry. And the intensity of the light coming down here rises and falls because of the relative motion of these mirrors, these going apart while those are going together. So I won't go into any more technical detail than that, but this is standard interferometry. But with the big hook, you've got these mirrors hanging from overhead supports and swinging, and you're bouncing the light back and forth many times. Well, I looked at this. I had not yet read the paper. I was in the final stages of writing a textbook on gravitation together with Charles Misner and John Wheeler, my PhD thesis advisor. I heard this idea. I did not actually read the paper because I didn't have access to it when I was finalizing the text in here. I didn't have access because Ray had not published it in a standard journal. He published it in an internal MIT report because his view was you should not publish about this until you had discovered gravitational waves. And so I'm serious. That was his view at the time. Of course, he changed his mind later. I looked at this idea, and I thought, this is not promising at all. And so this textbook, it says, there's a little passage in there that I wrote that says, this is not very promising. And let me explain why I said that. Let's talk about the distance of most of these mirrors back and forth. If you begin with 1 centimeter, about 1/3 or so of an inch, you divide it by a factor of 100, you get the thickness of a human hair. You divide by 100 again, you get the wavelength of the light that is used in these measurements. You divide by 10,000, you get the diameter of an atom. And you divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 1,000 again, you get the magnitude of these mirror motions. It's obvious that this is crazy. But I didn't put it that way. I just said it wasn't promising. And then I had long conversations with Ray. I read the technical details of his paper. I had long conversations with Latimer Burg, a superb Russian physicist who also had begun working on gravitational wave detection in the 1960s, like Joseph Weber. And I became convinced. And I wound up spending the majority of the rest of my career trying to help the experimenters pull this off. So I ate crow. Ronald Reaver at the Glasgow University, shortly after I became convinced, conceived an alternative design for these interferometers, which was fairly obvious to people who were experts in this, but that you could really pull it off successfully, as he showed then in the laboratory you could, was not at all obvious. So his idea was, instead of bouncing the light back and forth many times to make the signal stronger, making discrete spots on the mirrors, you let the light come in and you trap it between the mirrors in what is called a Fabry-Perot cavity, and then it leaks out. And so all these beams of bouncing light back and forth between the mirrors overlap with each other. And this turns out to have enormous advantages over Ray's original design, and that is the way we wound up doing it in LIGO. Ron also invented several other major things. For example, one of the key things that we needed to have in order to pull this off was to be able to stabilize lasers to a higher degree of stability than people thought was possible at the time. Ron pulled over from the microwave frequency technology the German idea that had been conceived and developed by Robert Pound at Forward, an idea where you lock the frequency of the laser, it turns out, in a certain manner to a stable mechanical cavity. And Ron then came here to Gila and worked with Jan Hall to prove it experimentally. This really did work. And so this is now called Pound-Drever-Hall locking. And that is one of the major contributions of LIGO to modern technology. So Ron was a major creative inventor for this. So in 1976 to 78, we had long discussions at Caltech about starting a research program in the field, a gravitational wave experimental program to complement my own theoretical program, and made the decision to go forward and brought Ron Reaver from Glasgow to start the effort at Caltech. We also brought Stan Whitcomb from Chicago, a young man who had previously been working in infrared astronomy, to join in and with Ron and the leadership. And they built a 40-meter prototype interferometer, 1% as long as we ultimately would build for LIGO. It still looks pretty damn long. In parallel with this, at MIT, Ray Weiss was completing the construction of a much smaller prototype gravity wave detector. But more importantly, he was leading a feasibility study for what were all the problems you would have to face when you tried to make these things big, several kilometers long, for these distances between the mirrors. And how much would it cost, and could you deal with all of the obstacles that you might run into? In 1984, with the positive results of Ray Weiss's study, the positive results of the prototype gravity wave detectors at Caltech, at MIT, and one in Glasgow, Scotland, that Ron Reaver had also built, and one in Germany that was led by Heinz Billings. With positive results from all those prototypes and the positive results from the the feasibility study for a big interferometer, Caltech and MIT got together and created the LIGO project. And from 84 to 87, LIGO was led by a troika of Weiss, Reaver, and Thorne. Now, troika in that era was a Russian phrase for a rather dismal leadership. And that was an understatement for our leadership. We were exceedingly dysfunctional. And so NSF, with the backing of Caltech and MIT, said, you have to have a single director who has the ultimate authority to make decisions and who leads this project. You can't run it with this kind of a troika. And so we brought on board Robbie Vogt, who had been the first chief scientist at the Jet Propulsion Laboratory at Caltech and had been the provost of Caltech. We brought him on board as director. He then forced the two teams, the group at MIT and the group at Caltech, to truly collaborate, which they really hadn't been doing. And he led us in the writing of a construction proposal for LIGO, a construction proposal in which we said we would first build facilities, big vacuum systems, to hold these interferometers, these gravity wave detectors. We would then have a two-step strategy for the interferometers. I use the word detector and interferometer interchangeably. They are the things that detect the gravitational waves. The two-step strategy, initial interferometers at a sensitivity where we would have to be lucky to see anything, but where we were quite confident that we could really build them and make them work. And then much more complex advanced interferometers at a sensitivity where we should see a lot of stuff. This two-step strategy was not a strategy that a number of people in the astronomical community could really understand or be sympathetic to. The idea that you would spend $300 million to build the facilities in the first interferometers and not see anything. And then you would have to build a new, better interferometers in order to have success. was just cut against the grain of portions of the astronomical community. So we were blindsided in congressional testimony, and we lost 2 years of basically a battle to get this funded. But in 1992, already in 1990, NSF began to back us. In 1992, Congress backed us. And Congress and NSF have backed us ever since with really no hesitation. And that's what really quite remarkable. When gravity waves were discovered, both the Republicans and the Democrats on the relevant congressional committees took great pride in their contribution to this. And I do have to say that both under the Republican leadership and under Democratic leadership over those decades, we had great backing from Congress. So this is really a triumph for NSF, for Congress, as well as the scientists. But for Congress, in behalf of the American people, it is true that you have spent $1.1 billion on this effort so far, and I thank you. So when it came time to move toward construction, we brought on board another director to replace Robbie Vogt named Barry Barish, who had far more experience in running very big projects like this, and who had a management structure that he presented that was far more to the liking of NSF, Caltech, and MIT, because it was the same kind of management structure as high-energy physicists have been using for some years, and Barish was one of the most accomplished leaders of high-energy physics projects. So Barry took over, and he led us through the construction of the facilities. He then designed the LIGO Scientific Collaboration, an expansion to include other institutions besides Caltech and MIT, because there was these detectors are so complex that it was hopeless for the small teams of Caltech and MIT by themselves could create and have those two institutions to pull it off. So it required many more scientists at other institutions. This collaboration is now 1,000 scientists and engineers at 80 institutions in 16 nations. And he led us in the construction and the first searches with the initial interferometers. He then was stolen away by the high-energy physicists to lead the design study for their next big high-energy physics accelerator after the Large Hadron Collider in Geneva. And so then we had a succession of two very strong directors, Jay Marks and currently David Wright, who led us through the final searches with the initial interferometers, which saw nothing, just as we had predicted they would see nothing. And we moved smoothly because we had promised NSF and Congress we would probably see nothing. We moved smoothly on to the advanced interferometers. 2010 to 2015, we installed these advanced interferometers. And just as we were about to turn them on, the first signal came in, but I'm not going to talk about that for another couple of minutes. First, I want to back off and say other things have had to come together to make this work. One of the other things, and these are things that grow out of theory, was in the meantime, on the theory front, Vladimir Berginsky, the Russian experimental and theoretical physicist whom I had mentioned before, he told us in 1968 that no matter what kind of gravity wave detector you would design, you would have to measure the motions, the dynamics of massive objects like LIGO's mirrors at a precision that is so great that you would discover that these objects are behaving according to the laws of quantum physics and not classical physics. And indeed, in LIGO, we monitor the motions of the center of mass of these two mirrors with a laser beam bouncing back and forth between them. And that center of mass, which is the thing we really monitor, it fluctuates randomly due to effects of quantum physics in the same way as the position of an electron inside an atom fluctuates, and for the same reasons. This isn't an electron inside a tiny atom. This is a 40 kilogram, a 100-pound object that you're seeing behaving with these quantum fluctuations. And this is because you are monitoring the motions of the mirrors to a precision in advanced LIGO, in the second generation detectors, that is approximately the half width of what's called the Schrodinger wave function of these center of mass degree of freedom. It's the level at which the Heisenberg uncertainty principle for 40 kilogram particles comes into play. So for the first time in advanced LIGO, as we move toward design sensitivity, and we're not quite there yet, we will be seeing human-sized objects behave quantum mechanically. And so I was a close friend and collaborator of Brzezinski's beginning in the mid-1970s, and we set up then a collaboration between my theory research group and his experimental research group, which also has some very good theorists in it, to develop what he called quantum non-demolition technology to deal with this. What are the techniques and the technologies that you need in order to be able to get a gravitational wave signal through some particles, 40-kilogram particles that are fluctuating their position? And you're trying to measure their motions when their position is fluctuating. How do you get the gravity wave signal through them without demolishing the signal due to these quantum fluctuations? So that's what's called quantum non-demolition technology. It's a branch of modern quantum information science. On the theory front, and I will return to that in a couple of minutes. On the theory front, there was a second issue, and that is computer simulations of LIGO's gravitational wave sources. It was essential that we have a capability to simulate colliding black holes, for example, because we could not predict the shapes of the waves, the so-called waveforms, the pattern of stretching and squeezing of the waves. By pencil and paper calculations, the only way we could predict it would be by solving Einstein's relativity equations on a supercomputer. And so colleagues of mine around the world had been working since the 1960s to perfect the techniques for doing this. I chaired the oversight committee, or the advisory committee, for the worldwide collaboration of computational physicists who were doing this in the 1990s, and I was aghast at how hung up they were. So in the early 2000s, I left the LIGO project in terms of day-to-day involvement in order to start a Caltech-Cornell collaboration, which we call the SXS project for simulating extreme space-times, to simulate collisions of black holes and other sources of gravitational waves, with the goal of having the capability in hand that we needed by the time gravitational waves were first observed. And we did succeed, but more or less just barely. The crucial breakthrough came from Franz Pretorius, who was a postdoc in my Caltech group in 2004. He carried out the first successful simulation of two black holes going around each other, colliding and merging. Then it took another 10 years to get the simulations so they were good enough to match the accuracy that LIGO required. This was crucial for LIGO's discovery, and it was in hand, and the movie that I showed you was produced by the SXS project. After the gravity waves were discovered, they went back to their and did simulations of what had been seen, and this movie is from those simulations. So September 14, 2015, about 3 days before our first gravity wave search with the advanced detectors was supposed to begin, a signal came in. The project was in the process of freezing the configuration of the detectors, bringing each detector into the final state that we wanted it in at the time of the first search. Not quite frozen yet. The first signal came in. The team froze the configurations right there when the signal came in. And officially then the search began at the time the first signal came. It was really quite remarkable. And the signal was large. This is the signal, the raw signal. This is the strain, the stretching and squeezing, the fractional change and separation of the mirrors, measured in units of 10 to the minus 21. So the amplitude was 10 to the minus 21. That was an amplitude that I and my other theorists were predicting was what we needed to, we would see going back to the late 1970s. So it turned out that we were right on in our predictions. This is the signal with the only manipulation of the signal that's been done is to remove everything above 350 hertz, for those who know this language, and below 35 hertz. So you have 1 decade of frequencies present in the signal. It's that bandpass filtering, as one says. That's all that's been done. The signal stands out very strongly. This is Livingston, Louisiana. This is in Hanford, Washington. Same signal at the two sites. When you clean the signal up, it looked like this gray trace. And then what was done was to go in and compare with computer simulations from the SXS project and from several other numerical relativity projects. Compare with those simulations, and you adjusted the masses and the spins of the black holes until you got a good match. And it was possible to get an essentially perfect match. And that perfection of that match told us that this really was produced by two black holes that were spiraling together and merging. And looking at the parameters, the masses of the black holes that gave this perfect match, we concluded then that the initial black holes were 29 solar masses and 36 solar masses. That's a total of 65 solar masses. You might ask, how do I define the mass of a black hole if there's no matter in a black hole? The answer is, it's by its gravitational pull. And that gravitational pull gives you a mass. That's how you measure the mass of the sun, is the gravitational pull on the planets, the orbital motion of the planets around the sun. The final black hole was 62 solar masses. 3 solar masses were lost. The final black hole was spinning 67% as fast as the maximum spin that is possible for a black hole. And the distance to the source is 1.3 billion light years. And all that came from comparing with the supercomputer simulations. We saw 2.9 gravitational black hole mergers in our first gravity wave search. Why 2.9? Well, 3 really, but one of them was sufficiently weak. We're only 90% sure that this was a real signal from colliding black holes. But we generally count it and use it in beginning to do statistics on black hole mergers. We saw the first one whose waveform, the stretching and squeezing as a function of time, looked like this. The second one that came in in 2015 on October 12th, and the third one on Boxing Day in England, the 26th, the day after Christmas in 2015. And each of them had its masses measured and the distance to the source measured. And we're beginning to do statistics then on the properties of black holes. These instruments are very complicated, as I told you. I just want to show you a little bit of photographs of the instrumentation. This is seen from the air, the Hanford Washington interferometer. The mirrors hanging from overhead supports are at the end here, at the corner here, and at the end down there. 4-kilometer long arms, inside vacuum pipes. The corner mirrors and beam splitter are in these chambers here. Barry Barish put that baseball player there so you could tell the size of the instrumentation. And this is one of the mirrors hanging from an overhead support. It's not locked in that cage, it's free swinging. The cage is part of the surroundings in order to control the environment. So you get a little bit of sense of the instrumentation, just a tiny bit. And as I mentioned before, there are 100,000 data channels, which means that each of these instruments has its own personality. And the experimenters who built the instrument, like the man who created Frankenstein, they only learn the instrument's personality after the monster has been built. And so the monster in this case was at only 1/3 of its design sensitivity when we made our first discovery. And why was it not at its design sensitivity? Well, it's a personality. Its personality is slightly different than the design personality. And so now the issue was to go in from February of last year to November of last year to poke and prod the instrument, trying to figure out its personality, trying to figure out what's wrong, what of many things are slightly wrong, and what combination of them is getting us in trouble, and begin then to, with that knowledge it's gained, to begin coaxing the instruments toward their design sensitivity. The LIGO team is in a process of doing this successive observations for a few months, then come down and poke and prod for a few months, then go back and observe for a few months. And this will continue onward then for between now and about 2020, when we should be at design sensitivity. So we are now in our second gravitational wave search. The first results from that will be published within the next month or so. But the data are still being analyzed, and to be absolutely sure that whatever it is might or might not have been seen really was or was not seen. And so I'm not allowed to say anything more than that. The future. By 2019 or 2020, we should be at design sensitivity. seeing 3 times farther into the universe than we do now. That means you see a volume of the universe that is 3 cubed, or 27 times larger than today, because we live in a universe with 3 dimensions. That's approximately 30 times larger volume, 30 times higher rate of observation of black hole mergers. The observed rate thus far is roughly 1 a month, 1 every 2 months, somewhere in that ballpark. And so we should be, by that time, be seeing a few a week, maybe 1 a day, black hole mergers in 2020. But we should also be seeing a number of other things. If the theoretical work that I and others, astrophysicists, have done is correct, neutron stars, stars made of pure nuclear matter, can have little mountains on their surfaces, little in terms of being high, maybe a centimeter high, but very broad, spreading over a big piece of the star because of the extreme gravity of the star. As the star spins, it produces what's called pulsar radiation that radio astronomers and X-ray astronomers see. But it will also, because of these mountains, produce gravitational waves. We will all see, and each neutron star like that has a diameter of about 20 kilometers, so roughly the size of Boulder, Colorado, and the density 10 times higher than the density of an atomic nucleus, and a mass, say, 1.5 times the mass of the sun. We will also watch the gravitational waves produced when a black hole and a neutron star go around each other and the black hole tears the neutron star apart. We will watch gravitational waves from neutron stars that go around each other and collide. If we're lucky, we will see gravitational waves from the core of a supernova explosion. This is where the core of a normal star implodes to form a neutron star. And then there is a gigantic explosion produced as a result. But theorists do not really know very well just how that explosion comes about. And observations of gravitational waves from this and neutrinos from the core of the supernova explosion will be crucial for figuring out how supernovae really work. And there are bound to be gigantic surprises sometime in the coming few years. And that's really the most exciting thing. And I can't tell you what those surprises are going to be, though I will make one speculation at the very end of the talk in a few minutes. I want to say a little bit about the science that we will be doing with gravitational waves before I bring this to a close, talking about 2 topics. First, exploring black holes with gravitational waves. Obviously, that's what we have begun to do. And then exploring the birth of the universe with gravitational waves. So those are my 2 remaining topics. Now, black holes are made from warped space and time. It's true that a black hole is believed to be created when a very massive star implodes after it's burned its nuclear fuel, and implodes so far that gravity becomes so strong that it will not let anything escape. And all the material of the imploding star goes inside the so-called horizon or surface of the black hole, and is basically, as far as we are aware, crushed out of existence in a singularity at the center of the black hole. That's at least what we think goes on. And you then are left behind with nothing but an object that is made from pure warped space and time. Sorry, am I all right? Can you still hear me? Okay. And so you can visualize this by looking in from a higher dimension. What I'll do is I'll take a black hole that's sort of a flattened sphere, if you were to look at it, and I'll take an equatorial slice through it and look at the geometry of that equatorial slice. And it's not like a flat sheet of paper. It is a curved geometry where circumferences are small compared to diameters. Instead, the diameter is bigger than the circumference instead of being smaller than circumference. If you want to visualize that, you take that 2-dimensional equatorial slice of the black hole and you imagine embedding it in a flat 3-dimensional space, like the space we live in. And it will have to bend down in the flat 3-dimensional space in order to fit in there. And this is the shape that you get. Alternatively, you can think of this as looking in from a higher dimension on the black hole. Black hole is the surface of this surface. The surface becomes flat far away. That's our external universe. The horizon is down here where it is black. and it looks like a circle, but it's really when you restore the third dimension, because remember I'm just looking at the equatorial slice, you restore the third dimension, that circle becomes a flattened sphere. So that's the horizon of the black hole. The color coding, so this shows the shape of the black hole. Circumferences in here are small compared to diameters going way down and back up. I show it only down as far as the horizon. The color coding shows the slowing of time near a black hole. Where it's yellow here, the transition from yellow to red, time is slowing at 10% of the rate that it is far away. And so that's right in here. And down where it's black, time is slowed to a halt. Those of you who saw the movie Interstellar, you see the effects on human beings of going down near a black hole, the aging of Murph, Cooper's daughter, the aging of Jessica Chastain, by comparison with Matthew McConaughey. So that's the slowing of time shown graphically in the movie. The white arrows show the dragging of space into whirling motion, fast near the horizon, slower much farther away. And this, in fact, depicts everything there is about the equatorial geometry of space and time around a quiescent spinning black hole. Now, LIGO is not the only kind of gravitational wave detector that we're going to have. In the next 2 decades, we will open up a total of 4 gravitational wave windows onto the universe. The analogs of X-ray astronomy, gamma ray astronomy, radio astronomy, and optical astronomy. 4 different frequency bands, all with gravitational waves instead of electromagnetic waves. Of particular interest is the Laser Interferometer Space Antenna, or LISA, which will have 3 spacecraft that track each other with laser beams that are several million kilometers apart instead of just several kilometers apart. Well, the gravitational wave pushes these mirrors back and forth with respect to each other, or these spacecraft back and forth with respect to each other, and the laser beams are used to monitor that motion. Because these distances are so huge, you can see gravitational waves with far longer wavelengths than LIGO can see, much lower frequencies. That means waves that are produced by much bigger black holes. And so, in fact, we expect to see gravitational waves from giant black holes in the nuclei of galaxies that weigh millions of times as much as the sun weighs. Now, suppose that we have a small black hole like the ones that LIGO has seen, say 10 or 20 or 30 times the mass of the sun, going around a big black hole, around and very gradually spiraling inward as it produces gravitational waves. Obviously, as it goes around, it does create ripples in the shape of space, and those go traveling out just as though you'd stuck your finger in a pond and stirred it around and around to create ripples on the surface of the pond. Those are the gravitational waves. It turns out that the gravitational waves that come off from this have encoded in themselves a full map of all aspects of the space-time geometry, the slowing of time, the dragging of space into whirling motion, the deformation of space, for the big black hole that's explored by the little black hole as it goes around and around. And I can make it plausible that the full map is in there by abandoning any attempt to show you the shape of space and just show you the small black hole going around the big black hole as though space were flat. But I want you to look at this orbit. It's nothing like anyone ever saw in the solar system. This is from solving Einstein's equations for the motion of the little black hole around the big black hole. The big black hole spins, and as it spins, it drags space into motion, and that motion of space, or in technical terms, the dragging of inertial frames, causes this orbit to get thrown around in manners that Kepler never conceived of. You have that going on, plus the influence of the curvature of space, plus the influence of the slowing of time. And that little black hole explores the whole region around the big black hole as it goes around and around for a period of a year or two. And as a fabulously strong student of mine showed mathematically, that gives rise to gravitational waves that do encode the full map. That student, Fenton Ryan, then left me and went to Wall Street. He didn't tell me that was where he was going until very late in his PhD career. But he has done very well there. Anyway. Now, what if the central body is not a black hole? For example, what if it's a naked singularity, like the singularity that's inside a black hole, but that does not have any horizon around it. It's not hidden inside a black hole. Well, John Greiner, who's a brilliant theoretical physicist in South Africa, has done a simulation where she computes the orbits of small black holes around a naked singularity that's sitting here. The one that's closest to the naked singularity, you look at that orbit, again, that's nothing like, it's nothing like anything you've seen, nothing like you see from an orbit around a black hole. It's truly a truly chaotic orbit, chaotic in the sense of mathematical chaos. You pose initial conditions and you cannot predict very far for how that orbit is going to behave, because its behavior is so sensitive to the initial conditions. And so you see the gravitational waves from that. It's obvious those waves are not from a black hole. They're from a naked singularity if they have that chaotic behavior. We also are already, in fact, exploring the dynamics of the geometry of space-time for colliding black holes. And we do this by the combination of the LIGO's observations and supercomputer simulations in the SXS project. So having seen which masses and spins for the initial black hole produced a waveform that matches perfectly what was observed, then the SXS team went back in and looked at the simulations and produced the movie that I first showed you, which is what it would look like to your eyes. But this is a movie of what it would look like to somebody looking in from the higher dimension. So you have the two black holes, funnels like I showed you for a single black hole, color coding the slowing of time, and arrows to show the dragging of motion, of space into motion. I'm going to slow this down. This is actual real time, 0.014 seconds, 0.013 seconds before the merger. And this is like a storm at sea, a gigantic storm with waves shooting up, the color coding in the red, time is flowing very slowly, then that goes crashing together and oscillates and dies out. And that's what produced 3 solar masses of gravitational wave energy. It was that gigantic wave that went up and back down with time speeding up and slowing down with the space distortion. And the waves then traveled outward. So we have looked at that in great detail in those kinds of movies, but we have also developed a variety of other ways to see what's going on with the dynamics of the shape of space and time. And this movie captures only a tiny portion of the space-time storm that's created by the colliding black hole. So that's a major area of research for my own research group at the present time, is trying to understand this dynamical behavior of space and time when the black holes collide. Well, I want to wind up with a few words about the birth of the universe. If we look out into the universe in all directions, we see coming from all directions microwave radiation that is left over from the Big Bang. And the photons of that microwave radiation bring us a picture of what the universe was like when it was just 380,000 years old. Earlier than that, the universe was so hot and so dense that photons, electromagnetic waves, could not propagate. They were trapped in the matter. They were scattering, they were being absorbed and re-emitted, and they were losing all the information they had. So the only information we can get about the universe with electromagnetic waves is back to an age of 380,000 years. Neutrinos, highly penetrating particles that I mentioned before in connection with supernovae, if we one day see them from the Big Bang, they'll bring us a picture of the universe when it was as old as at age 1 second, but not earlier, because the universe was too hot and dense for neutrinos to propagate before that. Gravitational waves are the only form of radiation that propagates unscathed, created in the Big Bang, and propagating outward, not absorbed or scattered significantly by matter at all, coming all the way to Earth, bringing us a picture of the Big Bang itself. So gravitational waves are our tool, our prime tool for exploring the first 1 second of the life of the universe. And that is going to be a major piece of gravitational wave astronomy over the coming decades. There is a lot of rich violence in the first 1 second, theorists think. I'm going to give you 4 examples and then I'll quit. First example is the Big Bang itself. It may well be, and this is the conventional wisdom, that the gravitational waves that came off the Big Bang were the minimum amount of radiation that nature allows. Just fluctuations, quantum mechanical fluctuations. But if that was the case, In the first tiny fraction of a second of the universe, actually the first 10 to the minus 34 seconds of the age of the universe underwent what is, we believe, what is called inflation. It expanded extremely rapidly. And that rapid inflationary expansion, theory says, should have amplified whatever came off the Big Bang to produce a rich background of gravitational waves. And that background of gravitational waves should have traveled out through the universe. And when the universe was 380,000 years old and was just cooling down enough that electromagnetic waves, microwaves as we now see them, were able to start to propagate, they will have placed, and by stretching and squeezing the hot gas then, they will have placed an imprint called polarization on the pattern of microwaves that are seen by astronomers today. So the so-called cosmic microwave background. That pattern has been seen. But there are other processes that can produce that pattern, the noise in effect, and the problem is to separate out the noise and really see what was it in terms of imprint created by these primordial gravitational waves. How much of that signal was really a gravitational wave imprint. And that is something that I expect will be sorted out within the next few years by people who work in the polarization of the cosmic microwave background. And so I do expect within a few years we will have our first observational data about the era of inflation and the Big Bang itself from gravitational waves, not by LIGO, but by this more indirect but very powerful route. Oh, here, CMB polarization. I said it, but I didn't show it. Second example, I expect that we will be watching with gravitational waves the birth of the fundamental forces of nature. The one we understand best is the birth of the electromagnetic force, the electric force and the magnetic force. When the universe was very young and very hot, there was no electric field, no magnetic field. The electromagnetic field is combined with what's called a weak nuclear force into a combined force called the electroweak force. And the laws of physics were different than they are today. When the universe was 10 to the minus 12 seconds, 1/trillionth of a second old, theory says that that electroweak force came apart and the electric field, the magnetic field were created, the weak nuclear force were created as separate entities. And this may well have occurred in bubbles in what is called a first-order phase transition at that time. These bubbles, according to theory again, had surfaces rather like the surface of a water droplet. They expanded, according to the theory, at the speed of light, collided, and produced gravitational waves. And in the many, many years since then, the gravitational waves, as the universe expanded, got stretched in wavelength until today they are in LISA's frequency band, the space-based gravity wave detector. So one of LISA's primary goals is to search for the gravitational waves produced in the birth of the electromagnetic force when the universe was 1/trillionth of a second old. LIGO can look for similar things, but it will see, we call this a phase transition. A phase transition changes in the laws of physics when the universe was 10 to the minus 22 seconds old. We have no idea what was going on in physics at 10 to the minus 22 seconds. But LIGO is looking for any possible gravitational waves that might have come from that. Third example, cosmic strings. These are defects in the structure of space. You look at the circumference around this string, and the circumference is less than pi times the diameter. That doesn't happen in ordinary space, even when you go up very close to the string. These strings may have been formed in the very early universe as linear defects. It may have been formed even by an inflationary expansion of fundamental strings, the building blocks of all matter. The key thing is that when two such strings collide, each of them stretching across the universe, collide, with high probability they reconnect, and you get a cusp on the string. Cusp goes traveling down the string at the speed of light, producing gravitational waves. And in this case, we know precisely what the shape of the gravitational wave is, and LIGO is searching for those gravitational waves from these so-called cosmic strings. Finally, our universe really might be a three-dimensional surface that lives in a higher dimensional space called a bulk. If it is, and this is completely speculation, wild speculation, if our universe was born crumpled up like this crumpled sheet of paper, then as time passed and this region of our universe discovered that there was a wrinkle between itself and that region, a huge tension in our brain, in our surface, in our three-dimensional universe. A huge tension causes the universe to straighten out like a drum head that you punch down on that, then let go. It goes flying back and vibrates, and those vibrations take the form of gravitational waves, some of which travel in our universe, and some of which travel out of our universe into the surrounding higher dimensional bulk. This is an example of the kind of huge surprise that gravity waves may bring us. I don't for a minute give this more than 1 part in 10,000 probability of being correct, but I offer it as an example of something that could be correct, an example of the kind of big surprise that we may have. So in conclusion, LIGO has opened up the first of 4 gravitational wave windows on the universe. We'll have the other 3 within the next 20 years. And they will become then, like the opening up of electromagnetic windows, LIGO in some sense is like Galileo turning his optical telescope on the sky for the first time, discovering the moons of Jupiter. LIGO turned on and saw the first colliding black holes. But there's been a lot happened in electromagnetic astronomy since Galileo, and there will be a lot will happen in the coming century and succeeding centuries with LIGO and their gravitational wave partners. Thank you.
Could we have the floor lights up, please? Professor Thorne has agreed to take some questions. We have microphones on stage left and stage right. So if you're interested, please.
But I won't let this go on very long. I spoke longer than I should have. I'm glad you appreciate it, even despite the length. But we'll have a few questions, but not very long.
So stage right over here.
Can you get closer to the mic? Oh, it's not on. Okay. Can the mic be turned on? Okay, go ahead and shout.
Since gravitational waves are fundamentally different in the way they propagate than electromagnetic radiation, how can you be sure that they are limited by the speed of light traveling by?
So the question is, since gravitational waves are so different from electromagnetic waves, how can we be sure that they're limited by the same speed of light limitation, that's the fastest they can travel? Well, Einstein says so. I appeal to authority. But it's not just Einstein. We now have a century of modern physics in quantum physics and classical physics, relativity. And we now understand, and this is verified for other forms of particles, that if you have a type of particle, a type of radiation that propagates and its strength dies out just as 1 over the distance from the source as electromagnetic waves do, then that has to propagate at the speed of light. It is carried by particles, quantum mechanical particles that propagate at the speed of light. Gravitons in the case of gravitational waves, photons in the case of light. I'm not saying this very well. What I'm really trying to say is that the laws of quantum physics, the laws of classical physics hang together. And they say that there are basically 2 types of radiation that you can have that has the form of classical waves, so that's carried by a boson field, and that then propagates at the speed of light, and its gravitational waves were carried by gravitons, and electromagnetic waves carried by photons. I guess this isn't much better than saying that Einstein told us so.
Stage left.
Oh, but let me just say, we do have observational evidence in the following way, that there are fundamental principles in physics, again, that say that if the graviton had a rest mass, it was not a massless particle, if it didn't propagate at the speed of light, then the gravitons that carry high-frequency waves would propagate slightly faster than those that carry low-frequency waves. That would mean the high-frequency component of the gravitational wave would propagate a little faster than the low-frequency component, and the wave would get distorted coming from the source to the Earth. The fact that the observed waves match so perfectly the simulations, it tells us that there was, to enormous accuracy, there was no distortion of the wave coming from there to here, and puts an amazingly sharp limit on the so-called rest mass of the graviton. Well, there is a time difference between the two measurement stations, but so we do measure the time delay in arrival of the signal of the two stations in Louisiana and in Washington, but that difference depends on the direction of the source. If the source were directly overhead, it would arrive simultaneously at the two. And so there is a and if the source was directly along the line of sight between them and traveling at the speed of light, then the time delay would have been, I forget the amount, but it's something like 10 milliseconds. It was 7 milliseconds, which tells us the direction of the source was in the south, but not along the line of sight.
Stage left.
I'm pretty sure that your answer to the last question answers my question too, but I'm going to ask it anyway. So, could gravitational waves escape from from beyond the event horizon of a black hole in the process of a merger?
No. So, the way the gravitational waves are produced, they are produced by the warpage of space outside the black holes. Just imagine two black holes as these funnels. They're going, and the horizons are at the bottom of the funnels. They go around each other, and it's the flaring part of the warped space that this black hole feels the flaring part of that black hole space, and vice versa. And it's the interaction of those flaring parts of the warpage that is giving rise to the gravitational waves. And that's all that action is occurring outside the horizon. So the gravitational waves are produced by that process outside the horizon, and nothing is coming from inside the black hole.
Thank you.
Stage left again.
Okay. Could you maybe talk a little bit more about the role of simulation in like ongoing projects and in future projects?
Yeah, so let me say that there are simulations are going on for a wide variety of gravitational wave sources, and they are crucial in this field. Essentially all the strong sources involve a huge amplitude of motions of matter or gravitational energy that simply cannot be analyzed with pencil and paper. And so simulations are the only way to understand what is predicted, and the only way to look at a wave shape, compare it with some prediction, and go back and see from the simulations what's going on. So the simulations, I talked about simulations of colliding black holes, simulations underway in the SXS project and many other groups of black holes tearing neutron stars apart, neutron stars colliding, simulations of the cores of supernovae, and the simulations of processes in the very early universe, such as the collisions of these phase transition bubbles. In fact, I have a concert that I have done with Hans Zimmer, who's the composer who wrote the music for Interstellar. He put together a 12-piece band, and I collected from about 25 astrophysical simulation groups around the world that are doing simulations of sources of gravity waves. Visuals of what the sources look like. Two colliding black holes, a black hole tearing a neutron star apart, these phase transitions in the early universe. And so we have something like 35 glorious simulations, which the team that did the visual effects for Interstellar has edited together to fit Hans Zimmer's music. And so we have this concert we've done twice so far of you just watch on the screen these fabulous, fabulous images of these simulations, all sources of gravitational waves fit to this marvelous music. And it's a real experience that has been great fun to do. So this is a major, quote, industry, but an industry of highly talented computational physicists who produce really beautiful visuals.
Science meets art. Stage right.
So the question is, can we use gravitational waves to discover primordial black holes? So primordial black holes are speculative things that conceivably could have been born near the time of the Big Bang if the universe was really chaotic in its structure then, instead of being very smooth, as conventional wisdom says these days. But they are things that we do want to look for. If black holes that were created in the birth of the universe really are there, that would change enormously our understanding of the birth of the universe. We do know, we think we know at least, that you can't have any black holes less massive than about 1.2 solar masses or so. That anything less massive than that is going to wind up as a white dwarf star or a neutron star. So there's some lower limit on the masses of black holes. If we were to see merging black holes where the masses were 1/10 of a solar mass, I think there'd be a very strong argument that these were primordial in origin. We don't know how to make such things in the modern era. So weighing these black holes is important in that sense.
Stage left.
So with photons, you see relativistic mass. With gravitons, would you also see relativistic mass from the energy that you've observed from the gravitational waves?
So the gravitational waves we know are carrying energy because there's 3 solar masses of missing energy. And that is, according to quantum theory, that energy is in the form of the energies of gravitons. And it's the same kind of energy as you have for photons. You stop a graviton and it loses all its energy, loses all of its mass. So the mass is entirely associated with the motion, actually with the frequency of the motion, the speed of light motion, the frequency of oscillation, according to quantum theory. And so it's identically the same so far as that's concerned as for electromagnetic waves and photons.
Stage left again.
Professor Thorne.
Would you call me Kip, please?
Okay.
My father is Professor Thorne. I'm Kip.
Okay. So Kip, I was wondering, continuing about the cosmic string theory. So, have cosmic strings been detected yet, actually, or is work being done to find cosmic strings, or is this purely theoretical?
So cosmic strings at the moment are purely theoretical. We don't know whether they exist or not. There are processes by which they may have formed in the very early universe, and there's been a lot of theoretical work done. There have been searches by a variety of techniques. There are limits on how much energy is in cosmic strings, but nothing has been seen yet.
Stage left again.
You stated that gravitational waves are not absorbed and re-emitted. So does that mean that that energy can't be converted into another form and it just sort of goes on forever and is essentially lost?
I should have said for all practical purposes. They're not absorbed and re-emitted. In fact, they are, but the absorption is so weak that the waves are able to propagate right out of the Big Bang with only a tiny amount of absorption and re-emission. And so, in fact, their energy can be converted into any other form of energy. And I can describe thought experiments for how to do that. But they're not thought experiments that where we have a prayer in the life of my great-grandchild to actually carry them out in reality and manipulate gravitational wave energy. It's just too weak an interaction.
Okay, there's, let's see, looks like 4 people still standing, so these last 4 questions, please.
So in the Tesseract, how does Cooper enter the Tesseract in the movie, and then how does he see different times of Murph's room?
Read my book.
I have been, and I can't comprehend it.
You read it and you didn't understand what I wrote. Yeah, well, I was afraid of that. So let me explain further. I'm not putting you down. That's the reaction of almost everybody. So I will just back off and tell Jan just a little bit. So Christopher Nolan conceived the use of the Tesseract, and he was the one who told me how it worked. And I then spent several months trying to translate that into a language that I understood, and going back and forth with him, and we iterated until we had a mutual understanding of how it could work. And then I tried to explain it, but not very successfully. So your specific question, again, go back about the Tesseract. Do you want to phrase it one more time? And my having said it took me several months to figure it out after talking with Chris. So the fact that you didn't figure it out reading 5 pages in my book, you shouldn't in any way feel like you're any dumber than I am.
So how does he enter the Tesseract through the
Okay, so that part in the movie, as he falls and he's deep inside the black hole, you see some white spots in a rectangular pattern. And those are the entryway into the Tesseract. Each white spot is a channel down into the Tesseract. So the Tesseract is basically an array of channels, perpendicular channels. And that's the opening. And so he falls into one of those white spots, which is one of the channels. You don't see him do that, but he does. And then then you next see him kicking and screaming at a intersection between perpendicular channels, what Chris calls a void.
Okay, cool. Thank you.
Okay.
Stage left.
That's the only part that I can explain in an understandable way. Okay, yeah.
I have a question about dynamics for you. Back to the part where you were mentioning 2 black holes orbiting each other, about to form a merger, and the orbit goes chaotic in the true mathematical sense. I want to ask you to elaborate a little bit more on that, and what that sort of dynamics tells us about mergers, and what your honest opinion on that is about, like, the true smoothness of our universe, and is it really smooth or not? If we're seeing those sort of
so let me back up. So the true chaotic behavior is what you see when you have a small black hole orbiting around a naked singularity rather than around a big black hole. And that says something about the nature of the space-time geometry of the big black, of the naked singularity. That it is really weird.
So are you hinting that the geometry of space-time could actually have a fractal element, like a non-integer dimensionality?
So it doesn't have a fractal element, but nevertheless you say a chaotic behavior of the orbits. It's not due to a fractal element in the geometry. It's just that the geometry is sufficiently weird that it produces orbits that behave chaotically. We do also see chaotic behavior as you approach the generic singularity in a very young black hole, what is sometimes called a BKL type singularity. The stretching and squeezing of space has a chaotic behavior. described by a mathematical map for those few people in the audience who may know about such things, a continued fraction mathematical map that is a chaotic map. And here it's the dynamics of space and time. The pattern of stretching and squeezing is chaotic. If you know the beginnings of it, you can't predict very far into the future because it's so chaotic.
So I just wonder if
But
we're
again,
missing
there's
something.
no fractal behavior into the structure of space and time involved in this, but there is in the dynamics. It is thought there may well be a fractal behavior to the structure of space and time in quantum theory on very small scales, but what you're seeing here is on much larger scales where the space and time behaviors are classical, not quantum, and not fractal, but nevertheless chaotic dynamics.
Interesting. I just wonder if we're leaving something out. Thank
What-
you very
okay.
much.
Stage left.
Hi. Yes, so if we go back in time to the beginning of the universe, the entropy of the universe decreases, and we have a very low entropy Big Bang.
You mean it decreases going backward in time?
Yeah.
Okay, which means
Well,
it
I mean,
increases going
is that-
forward in time.
Yeah, it increases forward in time. So if you go back backwards in time, you have a very low entropy arrangement. And so Roger Penrose has calculated the probability of that such a level of arrangement arising by chances, something like 1 part in 10 to the 10 to the 123 power. And so my question is, do you think there would be any chance of confirming that level of fine-tuning by looking at the gravitational waves coming further?
Yeah, I don't at the present time know how, but we're in an era where we don't understand the laws of quantum gravity that govern the birth of the universe. We don't understand very well the origin of the entropy of the universe. But we will understand those things, I'm fairly confident, through theoretical work, perhaps guided to some degree by observation of gravitational waves and other things, before I die. Now, I'm 77, but I intend to live to 110. So that's a prediction. There's an upper limit by which we will understand these things, so I will know about them before I die. But once we do understand the laws of quantum gravity moderately well, we can start asking these kinds of questions in an answerable way. At the present time, we just have hints that are intriguing and that Roger works on in this direction and that other people work on in other directions. These are great minds who have courage to work in an area that is still extremely foggy, and I follow with great interest what they have to say about it. But I'm just a gravity wave engineer, and I wouldn't have the guts to try to deal with those kinds of issues at our current level of knowledge.
Thank you very much.
Okay.
Is that a question at stage right? Okay. Last one at stage right, and then last one at stage left.
According to your talk, it's possible that a collision of the black holes can be more often than we thought before. So would it be possible that two collision events happen at a similar time and the gravity waves from those two events arriving the Earth at almost the same time? Are those waves actually interfere, or are the amplitude kind of being or resonant?
So the question is it possible that we could have enough black hole collisions that we have signals from different pairs of colliding black holes arrive simultaneously at the Earth? And would they then interfere? What would happen when they interacted with each other? For LIGO, in the LIGO frequency band, where we're looking at gravitational waves that oscillate with typically 100 oscillations per second, these things are sufficiently rare that that's very unlikely to be seen in the next decade anyway. But in the LISA frequency band, where the gravitational waves from colliding black holes oscillate with periods of hours or days, we will see that. We're essentially sure we will see gravitational waves from a large number of black holes that are spiraling toward each other and then colliding in the universe simultaneously. And what the theory says is that those waves are like very weak waves on the surface of a pond. They pass through each other and interfere with each other. And where two crests coincide, you get a higher crest. Where two troughs coincide, you get a lower trough. Where a crest coincides with a trough, they wipe each other out. But they pass through and they're unscathed. They're unchanged after they pass through each other. They undergo what we call a linear superposition. And that's what the prediction says. And so there's no real interaction, just a linear superposition. There remains the issue of, well, how do you figure out what's going on with these waves if you have them simultaneously? And the answer is that there are techniques that have been developed and proved out by the data analysis team that's working on LISA for peeling these waves all apart. And it's very similar to tuning a radio to a particular frequency in order to pick up a particular radio station or a television set. You know in advance for black holes of binaries with various masses and spins, you know what the wave shape should be. You search for those kinds of wave shapes, and you can readily find two different wave shapes, even if they're overlapping with each other, if you know what you're looking for in advance. It's by tuning in. It's called technically the method of matched filters. So this method of matched filters has been developed to a fairly sophisticated degree, whereby what is actually will be done in LISA is you take the strongest signal, you identify it with very high accuracy, you remove it from the data, and then the next strongest signal, identify it with very high accuracy, remove it from the data, and so forth.
Last question.
Perhaps we could end on just a slightly different topic. Could you share your perspective on what you think dark matter and dark energy is and why we haven't been able to directly observe it?
I have no wisdom about that of my own. My colleagues who are much deeper in this than I tell me that the dark matter is very probably fundamental particles, but of a different sort than have been created in particle accelerators thus far, that we can interact weakly with ordinary matter. Dark energy, they think, is very likely a manifestation of vacuum fluctuations, of things like the electromagnetic field. That's the sort of establishment explanation. I have seen the establishment go wrong enough times during my career that I would not be terribly surprised if they're all wet. But I would also think that the odds are pretty good that they're right. We just need more data.
Thank you.
Thank you for coming tonight. Drive safely.